for sodium azide here, one thing we realized when we looked at the molecule was this is a molecule that's going to have ionic bonding. So that leads you to want to disassemble the molecule into two ionic pieces, a cation and an anion. So you're going to clearly have sodium as a cation and azide will be the anion. It's important in this structure to do that because once you've done that, you now have a negative charge on the N3 piece, and that's going to affect how you ultimately build your Lewis structure. So the next thing is to think about connectivity. In our instructions over here on the other screen, we need to know the atom connectivity. And it is actually possible to conceive of other ways to draw N3. You could draw a little triangular ring maybe, but beyond that, it seems pretty clear that three nitrogens have to be somehow attached to one another. And since you have three nitrogens, you move on to the next step now that you know the connectivity, and that is to figure out the number of valence electrons that are going to be in the molecule. To do that, you need to know where in the periodic table nitrogen is. You need to know how many electrons are going to be in its valence shell. So it's got a couple in the 2s and 3 in the 2p, so that adds up to 5 valence electrons for each nitrogen. So in our bookkeeping here, we take 3 nitrogens, all with 5 electrons. That gives us 15. And then we don't forget about the extra electron that's going to allow this N3 to be negatively charged. So we add 1 more to the charge. If you had a cation, you subtract 1 from the total. And if your molecule is not charged, you don't do anything here. So since it's negatively charged, we add 1. We get 16 electrons. And that tells us how many electrons have to be explicitly shown in our valence structure, or in our Lewis structure, pardon me. And so down here, we built the structure, and we did it 2 different ways, one with dots and one with lines. Both are acceptable to do. We started out by just connecting together the nitrogens with 1 pair of electrons. And then we distributed the remainder of the electrons on the structure. We didn't talk too much about how to do that last class. But there are a couple of useful things that you want to recognize as being goals in drawing Lewis structure. So one goal is to try to fill as many of the valence shells as you can. So for most of the atoms we're going to talk about, that means getting 8 electrons around each atom, except for something like hydrogen. And so if you look at the nitrogen on the left here, we can see we've got our nitrogen, 2 electrons above, 2 below, and then these 4 in between the 2 nitrogens. Those are all the electrons in the leftmost nitrogen's valence shell. Okay, so it's got a full shell. And you could go through and try to fill the valence shells of all of the elements in the structure. If you find that you maybe don't think you're going to have enough electrons to do that, the thing that you should do in distributing the electrons is to try to give electrons to the most electronegative atoms first and the most electropositive elements last. So here we've got 3 nitrogens, so they're all the same in electronegativity. There's not a lot of choice. But if we had nitrogens and oxygens, we would tend to give the electrons to the oxygen first because it's more electronegative. So you go through and you do that. We manage to fill all the valence shells for each nitrogen here. And the last thing you do is you do this formal charge calculation. You need to have 3 numbers to do that. You need the number of electrons in the valence shell of the neutral atom. And that's what you used in your calculation up here. So you already know that number. So 5 is going to appear in all of our formal charge calculations for nitrogen. Then you need the number of non-bonding electrons, and these are the electrons that are pairs or single electrons that surround the atoms but are not involved in bonding. So the two pairs in the middle here, we're saying are bonding those two nitrogens together. So those are bonding electrons, but the other 4 electrons are non-bonding ones. Those non-bonding electrons, we say that the nitrogen possesses those completely. So it has 100% ownership of those electrons, so that would be 4, but it only has half ownership of the electrons that are involved in bonds. So they're effectively thought of as being covalent electrons, so we get half of the 4 here. So I wrote the final answer down, but I didn't write down the calculation. So here was the formal charge for this nitrogen, but we can also go through and do the calculation like we just discussed. So 5 electrons in neutral nitrogen's valence shell minus 4 non-bonding electrons that it has full ownership of minus half of the bonding electrons which are shared. So the result of that calculation is once again minus 1. You have to do that for every atom in the molecule. After a while, you start to look at atoms and say, oh, I've seen this type of atom in this arrangement before. I see I've got a hydrogen. I've got 1 bond to the hydrogen. That's going to be 0. Zeros you don't have to draw in the structure. So if you can look at your molecule and say, I recognize most of the situations here, but there's just these few that maybe I have to double check the formal charge on, that will get you to completed structure pretty quickly. You have to get the formal charges on, though, to have a complete structure. The final thing that I'm pretty sure we didn't talk about last class that I'll mention now is that if you look at this azide anion, N3-, it's N3-. The overall charge on azide is -1. And so if you look at the Lewis structure here, you'll notice we have a formal charge of -1 on each of the end nitrogens. We have a formal charge of +1 on the middle nitrogen. You add all those together, plus, minus, minus, you get -1. So the formal charge of all of the formal charges add up to the charge that the original structure would have had.